Hello, my name is Dr. Sean Riley. I am a physical therapist and certified wound specialist, and today I'm going to be presenting on nerve signaling and the resting membrane potential. So as we start talking about the electrical nature of neurons, there are some basic concepts we need to talk about first. And that would be that neurons are going to initiate and conduct electrical signals called nerve impulses. So that nerve impulse is a wave of electrical fluctuation that's going to travel along the plasma membrane. Now remember that plasma membrane is the outside layer of the cell that this waveform, again, is going to be traveling on. And these neurons are going to have to exhibit both excitability and conductivity. So what that means is we have to have a way to excite these neurons to get them to express a behavior, and then they need to be able to conduct that impulse to the next neuron and the next neuron and so on until we get to that target tissue and get our desired outcome. So to talk about membrane potentials, at rest, we're going to see that there is a slight excess of positive ions on the outside and a slight deficiency of positive ions on the inside, or the inside is going to be slightly negatively charged. Now, this difference in electrical charge is called the potential because it's a type of stored energy or potential energy. It's not doing much, it's just there at rest. It's there for when we want a desired outcome. And one thing we have to think about is we want these membranes to be containing a charge, because if they were just balanced, we would not be able to have something go forward. So that polarized membrane is again having that potential. The opposite ions are going to be held on the opposite sides, meaning the positive charge more so on the outside, and again the inside is slightly negative. So the magnitude of the potential difference between the two sides of a polarized membrane is going to be measured in volts, or oftentimes millivolts. We're using a voltmeter to measure the voltage across the membrane. You may be asking yourself, why are we talking about this machine that's measuring the volts? Someone like myself, I'll oftentimes get stuck on something as simple as this and want to know why we're measuring it or how we're measuring it. So I find it's useful to enter this information. You're also going to see a sign of the membrane's voltage that's going to indicate the charge on the inside surface of that polarized membrane. Again, now we're talking about the inside surface. So our resting membrane potential is that potential maintained by a non-conducting neuron's plasma membrane. So again, this neuron is at rest, and it's typically about negative 70 millivolts. So that slight excess of positive ions in the membrane's outer surface is produced by the ion transport mechanisms and the membrane's permeability characteristics. So that's where we start talking about these gated channels that allow diffusion across the membrane when that gate opens. Not all membranes are going to be have the same type of permeability. We're going to want to control what's going in and out of these membranes. So it's a good idea for each of them to have their own unique characteristics. So in a resting neuron, we have these potassium channels. They're going to be open, allowing that potassium to diffuse down its concentration gradient, meaning out of the cell. And then that's going to add an excess of positive ions on the outer surface of the plasma membrane. So remember, the outside is already more positively charged than the inside. The outside is now becoming more positively charged. Sodium channels are going to be closed, which prevents the diffusion in the opposite direction. So it prevents that sodium on the outside from rushing into the cell on the inside. And these channels for the transport of these major ions, or the negative particles, are either non-existent or closed. So as you see in this depiction here, we have a chloride ion on the exterior aspect of the cell. There's no channel for that to move in and out. So the way that the polarity of these the polarity of these neurons are changing is by the flow of positive ions, not the flow of negative ions. So we mentioned this sodium-potassium pump it's a sort of active transport mechanism in the plasma membrane where it's transporting the sodium and potassium in opposite directions at different rates. So the unequal rate is 3 to 2, meaning 3 molecules of sodium to 2 molecules of potassium. It's going to help to maintain that imbalance in the distribution of positive ions, and as a result, the inside surface becomes slightly negative with respect to its outer surface, as we were previously discussing. Now, we can't talk about nerve depolarization without understanding local potential. So this local potential is a shift away from the resting membrane, but only in a specific region of that plasma membrane, not the entirety of the plasma membrane. And we get excitation here that occurs when a stimulus triggers the opening of additional sodium channels, causing an excess of positive ions on the outside to decrease. So those sodium ions are now moving into the cell, allowing that potential to move towards the zero mark, which is called depolarization. So we also have these stimulus-gated channels that are ion channels which open in response to a sensory stimulus or chemical stimulus from another neuron. These are located in the neuron's input zone, which are known as the dendrites and soma, or cell body. So where we have the ability to create an action potential, we also have the ability to move further away from one. So that's where we talk about the thought of inhibition. So this occurs when a stimulus triggers the opening of additional potassium channels. So this is going to do the opposite of when we open those sodium channels, meaning we're now getting an excess of positive ions on the outside of the nerve. So this is going to increase the membrane potential away from zero or below the resting membrane potential. We call this hyperpolarization. So if we're talking about that resting membrane potential being at negative 70 millivolts, we're moving more towards negative 80, negative 90 millivolts, so further away from that depolarization mark that comes with moving more positively. So these are called graded potentials because the magnitude of the deviation from the resting potential is proportional to the magnitude of the stimulus. So the more stimulus, the more fluctuation we get. So these can be large or small, and they're not going to be all or none events. There is a gradient to what's happening here. So these local potentials are going to show decremental conduction, which means that their magnitude decreases as they travel along a membrane. Think about a wave in the ocean. As that wave is rather large when you see it in the distance, as it crashes and gets closer to the beach, it gets a little bit smaller. That's sort of what's happening here. These local potentials, because they are spreading over the entire plasma membrane. So as we see here, it says that they're called local nerve signals because they are more or less isolated to that particular region of the plasma membrane. Those local potentials don't spread all the way around to the entire nerve axon. Now we talked about depolarization and hyperpolarization, so that excitatory stimuli that's causing depolarization. So it's moving towards it's moving towards 0 millivolts. As you see on this depiction here, we have that resting potential as the red line, and those local depolarizations. See, they're not moving all the way up to 0, but they are causing a wrinkle in that line that we're seeing as the depolarization. Now, the inhibitory stimulus is going to cause hyperpolarization. They're those local deviations away from 0 millivolts that cause the membrane potential to dip below the level of the resting membrane potential. So you can see this also here as the local hyperpolarization is depicted on the right side of this image. So again, our action potential is the membrane potential of a neuron that is conducting the impulse. So the mechanism that produces the action potential occurs when an adequate stimulus triggers the stimulus-gated sodium channels to open, allowing that sodium to rapidly enter the cell and cause a localized depolarization. As that threshold potential is reached, the voltage-gated sodium channels are going to open to allow more sodium to enter the cell, causing further depolarization. So there's sort of a threshold here, and that's where we get that threshold potential, where the minimum magnitude of a voltage fluctuation at the summation area, also known as the axon hillock, or the conduction zone, being the axon, must have to trigger the opening of a voltage-gated ion. It's sort of, we open a little bit. Once we hit that threshold, we can now get a full rush of sodium entering this cell. So these voltage-gated channels, they're ion channels that open in response to that voltage fluctuation. Now, as we continue with this, we see that the membrane moves rapidly towards 0 millivolts and continues in a positive direction for a peak action potential of positive 30 millivolts due to that excess positive ions inside the membrane. Now, again, that is those sodium ions. So it's a rapid fluctuation because that sodium rushes in. Now, we talked about on the previous slide the sodium gated channels opening. Now, if the local depolarization fails to cross that negative 59 millivolt threshold, those voltage-gated sodium channels, they don't get to open. So in order for this to happen, we need to move from a negative 70 millivolts to a negative 59. We need a positive 11 movement in order for this to happen. So those voltage-gated sodium channels stay open for only about 1 millisecond before they close. Now, these are an all or none response, unlike the local potentials. So after the action potential peaks, the membrane begins to move back towards the resting membrane potential, that negative 70 millivolts, when those potassium channels open, allowing that outward diffusion of potassium, and this process is known as repolarization. So the brief period after hyperpolarization occurs when there's too much potassium rushing out. At that point, the resting membrane potential is restored by those sodium-potassium pumps. So if we take a look at this illustration here, we can see we're starting off at the negative 70 millivolts. We get the stimulus for those sodium channels to open. Those sodium channels then reach that voltage-gated threshold of negative 59 millivolts. At that point, the sodium rushes into the cell, causing rapid depolarization. We then follow it with repolarization as the curve comes back down to the resting threshold, and as you see on the right side here, it dips down a little bit lower than negative 70 before resurfacing back at that negative 70 resting area, again fixed by those sodium-potassium pumps. So we do need to speak about a couple things called refractory periods, where we have the absolute refractory period is going to be that brief period during which a local area of the axon's membrane is going to resist restimulation and will not respond to a stimulus, no matter how strong. Now, this period is about half a millisecond. Remember, those channels are only open for about 1 millisecond, so these are very short periods of time. At this absolute refractory period, we are not going to get a stimulus from this neuron, regardless of how strong that stimulus is. Now, the relative refractory period, this is the time during which the membrane is repolarizing and restoring its resting membrane potential. It occurs a few milliseconds after that absolute refractory period, and it requires a very strong stimulus in order to get a response from the membrane. At this time, I would like to thank you for listening to my lecture on resting membrane potentials, and here is my contact information in case you have any questions. Thank you again.